Okay, part 2 of alkane nomenclature, rings. Rings are the focus of this one. That gets kind of fun. These are the ring sizes you want to be comfortable seeing alkanes close into. 3, 4, 5, 6, 7, and 8. And you're used to calling these probably by their geometric shapes. Triangle, square, pentagon, hexagon, right? All the way up to octagon. These are the ones you want to draw easily, quickly, and be comfortable naming regularly. We will get rings higher than 8 for sure, but by far the most common you'll see very frequently are 5, 6, 7. That doesn't mean we won't draw 3 and 4 membered rings a lot. We will, or 8 membered rings, but 5, 6, 7 are the most common, and that's because they're actually more stable. Why? That geometric shape represents a certain angle you can calculate. The angle needs to be compatible with the bond angle that carbon likes to adopt. We know that if these are alkanes, that bond angle should be tetrahedral, 109.5. So of these three, of this set, these three are the closest to that ideal angle. Okay, once you stray, this is too big. These are too small, like 90 degrees, way too small. 60, way smaller than 109.5. These are more strained and therefore higher energy, less stable. Okay, we will get to that in great detail, but for right now it's naming, so we'll get to the stability later. Cycloalkanes are named with the cyclo plus the Greek prefix hex, but, prop, and then the ane. So we're just adding the cyclo, in other words. So for example, cyclopentane is that part, but it's going to have groups on it. There's no way most of the time you're not going to have just the ring by itself. So how can we name this? Well, this is the parent now. The cyclopentane is the parent. But it has a group on it, and we don't need to number this one. We do need to number if there's more than one, because by default, this would get number 1, because you always want the groups to have the lowest number. So this would be 1-methyl cyclopentane or just methyl cyclopentane. You'll notice when you do your ChemSpider searches, synonyms are common for naming. As much as we try to make it exact, and look, I did that space on accident, which is why it is hard. My logic likes to find the parent name first, but then that often makes me write too big of a space. There's really not a space there. Methyl cyclopentane. Okay, so yeah, synonyms are a thing. You'll see synonyms for chemical names, but at least we are still pretty powerful that we're able to narrow down the correlation of structure with very few names out of all the possible isomers. What is that? That doesn't even look like any of those geometric structures. Well, like I said, those bonds can bend, rotate. They are single bonds. They can adopt other conformations. That means they can squish close together. They can stretch way out. It depends on their environment for the most part, but it turns out this is actually the most stable way this ring could be sort of arranged. If you look down the center of a cyclohexane ring, you are going to see that it actually, when you turn on its side, it looks like this. So that's cyclohexane. Let's number it just to prove it. 1, 2, 3, 4, 5, 6. That's a 6. That is a cyclohexane ring. This is called the chair conformation, which we will spend a lot of time on. That's why I use that as an example. Okay, let's do another one. Okay, if you think the parent name is propane, you're almost there. Cyclopropane. All right, so let's number it. We have 1, 2, 3. Let's number the other way. 1, 2, 3. I'm making sure I start with a 1 on one of the carbons that has a methyl, because I know there's no way this carbon's going to be number 1. It's going to be a carbon with a group. You want to give the lowest numbers to the carbons that have groups on them, right? So we might as well start with Might as well find a carbon with a group on it and start number 1 there and then see what other options we can come up with. So I have a red option or blue option. The red option tells me I have 1,2-dimethyl cyclopropane. The blue option tells me I have 1,3-dimethyl cyclopropane. I think we agree it's red is better. So darn, I wrote in blue. I'm going to trace over it. There's no confusion. So 1,2-dimethyl cyclopentane. Propane, excuse me, propane. Now I want you to break out your model kits and take a minute to build that model, build that molecule. I'm going to give you a tip. You're going to need the long bonds that usually we use for double bonds because it'll prove how strained this ring is. So go about build it before you come back. Okay, if you built it, you're going to see this. The 2 methyls could be on the same side of the ring. See, here's my methyls on the same side of the ring. Or I built the other one too. The 2 methyls could be on opposite sides of the ring. That's what it looks like here. One coming out at you, one going behind. So those are 2 possible ways to build it. Did you get both of those? Let's convert the model to drawing with dashes and wedges. Okay, so if the methyls are both on the same side, if I turn it towards you, which one was it? This one. They're coming out at you. So I'm going to write Me just to make it extra clear that those are methyls. And you don't need to draw the H's, but you can. You want me to draw them? Okay. I could have said, well, maybe I wanted to draw this one. Fine. All I did was turn the molecule around. Now the methyls are going away from you. So that just, when I look at this fancy arrow I just did, an arrow with a loop in it, that means I flipped it or rotated it. And often we write the operation over it. Flip over. Or 180 out of plane rotation. Out of plane rotation. This is going to be our thing for a while, is 3D analysis. You want these models. You want to be comfortable with them. You know, if you're doing it right, they're actually a crutch and you don't want to get rid of them. So get over that barrier to start using them. Use them right away. So flip over, what do I mean by that? So methyls coming out towards you. Out of the plane, rotation. It's really like a pancake flip, right? Now, only the H's are coming towards you, the methyls are going in the back. All right, so that means they're the same. If you can rotate it, flip it, whatever you're doing, and it's the same molecule, then you did not draw something new, even though it looks like something different. So both dashes is exactly the same as the both wedges. But I had to literally break a bond. I'd have to break off one of these methyls. See, here's this where they're on the same side. I have to break one off and trade places with this H to get the other model I had built. So I want you to do that. It's where they're on opposite sides. So that means one methyl is a wedge, the other is a dash. And we should always say, well, can I have the other scenario? Can I have the methyl on the left be a dash and the one on the right be a wedge? That's a wonderful question that you should always ask. Okay, can we say those are equal? You need to build models of both and prove it to yourself or visualize can I take one and put it on top of the other? That's called superimposing. Can I superimpose one on the other and have the same thing? So let's move this one over here. Nope, they don't go right on top of each other because on the left is a wedge, on the left here is a dash. What if I do a pancake flip? Pancake flips make dashes, wedges, wedges, dashes. So they also make right, left, and left, right. So if I flip this one over, that one goes from this side to this side. And it becomes a wedge. So a wedge on this side does not match this one, so it does not superimpose. Try that yourself with a model. You can also do it in Spartan, which is my lazier way of doing it sometimes because the models take a little longer, but I want you to be comfortable with both. They both have their place. So here, which one is this? Which one does this go with? So notice the methyls are coming out toward you. So that matches this one right here. So what about this one? Which one does that match? Take a minute to look at that. There's a methyl on this side coming out at you. The H is the front atom here. So that would be a dash methyl. This would be a wedge methyl. So that one matches this one right there. I built the other one too. So I hope this is the same. Ooh, I put it over here. Oops, right there. Wedge on the left, dash on the right. This is wedge on the right, dash on the left. See how that methyl's going behind the H here? So that would be this one. And this methyl's going behind the H here. So that would be this one. Or in front of the H here, excuse me. So that'd be this one, wedge. So those are not superimposable. So they're different. Oops, let me move this model out of the way now. So we're going to acknowledge that they're different. We have an entire chapter, that's hard. So we have an entire chapter coming up called stereochemistry. These are stereoisomers that focuses on this difference. But just for now, I want you to kind of be aware that just because you have the same connectivity doesn't mean you have the same isomer. You can actually have different isomers. So these are called stereoisomers. What you should know is that these are clearly different. Right now we can observe that. So for now we are going to focus on distinguishing why the black is different from the blue, but in a later chapter you will know why the two blue are different in more detail. So for now, temporarily, we are going to use the simple way of naming these as opposed to the way we'll use it in stereochemistry chapter. So if these groups are on the same face of the ring, like the methyls, they're either both behind the ring or both in front of the ring, we'd say they're cis. You've probably heard that term before, right? And it's italicized usually, so I put a little underline there. The prefix trans will tell us that they're on opposite sides of the ring. Okay, so let's label the cis and the trans. Okay, so now let's add those names for them, okay? So all isomers of dimethyl cyclopropane. Well, first of all, you can actually put both methyls on carbon 1. So you have 1,1 dimethyl cyclopropane, right? 1,1 dimethyl cyclopropane, because it didn't specify what numbers they would be on, because that'd be carbon 1. But we can also have, we knew that these were named 1, 2 versus cis and trans, right? So here's a trans one and here's a cis one. There's a 1 and a 2, a 1 and a 2. It doesn't matter which one you pick. So since these are on opposite sides, we're going to add a trans to that. 1, 2, dimethyl, cyclo, ooh, that's long, propane. So that's this one. And this one would be cis. Put a little underline for the italics. 1, 2, dimethyl. And then I'm running out of space, so I'll write cyclopropane below. That's okay to do if you have to. Why did we do that? Because drawing the 1, 2 version once you build a model, you realize 1,2-dimethyl cyclopropane has more than one isomer itself. So that constitutional isomer, the 1,2 constitutional isomer, has stereoisomers, ways that these two methyls at the 1,2 position could be arranged different in space. Okay, so I'm going to write that here. These are stereoisomers. All right, we'll get into stereoisomers in much more detail later, but that's what happens when the constitutional isomer looks the same because it's a 1,2 position. They're connected in the same order, but they're spatially different. The methyls are both out or opposite each other. Let's do some more naming. Now, here are some cyclic structures. Notice some of them have dashes and wedges and some don't. Does that mean these don't have stereoisomers? Absolutely not. These could have dash dash, wedge dash, wedge wedge, dash wedge, dash dash wedge, wedge dash dash, wedge wedge dash. You can have all of those as part of the collection of stereoisomers, but it's not defined. So you're going to have to just name it as a constitutional isomer of that cycloalkane. So in other words, this is a cyclohexane parent, and we got to number it. Always start with a carbon with a group on it. 1, 2, 3, 4. I can stop there. So now I know it's a 1-4 relationship, but if it makes you feel better, you can go to 6. So you could write your cyclohexane. I'm going to write it below because I feel like I want to write it big enough. Okay, 1 and 4 position each have a methyl. So 1,4-dimethyl cyclohexane. No cis, no trans. It wasn't defined. There's no dash or wedge. So same idea here. Cyclohexane, but this time we have 3 methyls. So we're going to do trimethyl. Let's number it. 1, 2, 3, 4, or 1, 2, 3, 4. Now, I could also have gone the long way, 1, 2, 3, 4, 5, but you notice I didn't go up to 5 in any of these routes, so that's not the ideal path. Which is better, a 1, 3, 4 trimethyl pattern or a 1, 2, 4? 1, 2, 4, right? So we're going to pick the black path. 1, 2, 4 dash trimethyl cyclohexane. Now, the next one, we do have wedges present, so we have to use the cis descriptor because it's specifying which stereoisomer of that constitutional isomer we have. So what kind of constitutional isomer is it? What number pattern is it? Look at these groups, by the way. How do we name those groups? Those are carbons 1, 2, 3, but that's not a normal propyl. So that brings up another point. I use this one because you might have seen the isopropyl group before because it's so common. So that's isopropyl. When it has that branch, that's versus regular propyl. So that's N-propyl, or just propyl. So 2 ways to have a substituent with 3 carbons. So we're going to use isopropyl. For branched substituents, you're going to use their nickname or their common name as opposed to subdividing and naming those branches if possible. So we have 2 isopropyl groups. They must be cis to each other. And the smallest numbers we can manage to work out, hopefully by now you can see, is 1, 3. So let's do that. 1, 3 di-isopropyl cyclo, get back here, hexane. Are there other groups that we should know that could have that branch pattern? Can butyl have some branch nicknames? Yes, it can. So these are the ones you want to know. Okay. The rest you would have to just look up, but these are the ones you should know fast enough to do this as you name them. Okay. What I'm going to do here, just for some practice, I'm going to draw a big, long parent. Let's see. I'm going to do this up here. I'm going to zoom in. Let's start over, make it nice. I'm also going to use a fatter stylus. Okay. So let's go here. 1, 2, 3, 4, 5. It doesn't really matter how many because I'm actually not going to name it. I'm going to focus on all the substituents we could have and the beauty of this paper that allows us to have those perfect bond angles. All right, so now let's draw in some groups, our different groups. Let's start with the propyls. I'm going to draw a group here, and in red, I will actually just do it all in black. 1 carbon added, 2, then 3. That's your propyl. We could also have an isopropyl. So we've learned those, right? Let's write out those names. So 1, 2, 3. When it goes straight in a line like that, that's your N-propyl, also called NPR or just PR, capital P, little r. This is isopropyl. IPR is usually the shorthand for that. Okay, now let's do the 4 carbon chains. I'll do those up above just to switch it up. Okay, so we can do 1, 2, 3, 4. Let's see other ways we can, I'm actually going to number these. 1, 2, 3, 4. Now, we didn't have to attach it to that first carbon and make a linear chain. We could have branched it. So what if the point of attachment was here? So let's write that out. I'm going to make a bigger one. 1, that's too big. 1. Now we're going to attach the butyl. Let's put it here. 1, oh, that's an eraser. 1, 2, 3, 4. It's attached to carbon 2 now. Hopefully you see we get the same thing if you attach it to carbon 3. So let's compare those. The one where it's attached to carbon 1, that's your N-butyl, or just BU sometimes. The one where it's attached to carbon 2 on the second carbon is sec-butyl. And that's italics. We have another way to arrange those 4 carbons, and that's tert-butyl. I'm going to do this in black. If you number that, you should count 4 carbons. 1, 2, 3, 4. So that's called tert. For tertiary, tert-butyl. Also called T-butyl. It's a common one. The only one I'm going to bother to bring up is the 5-membered one. Other than pentyl, let's do the pentyl. You don't have to know all of the 5, but I'll give you the one that's we'll see quite often. So 1, 2, 3, 4, 5. That's regular pentyl. But if you go this way, 1, 2, and then you branch out right there, you have, well, that's actually missing a carbon. That way. That's isopentyl, but we didn't do isobutyl. That reminded me I missed one. So 1, 2, then branch out. So you could have all these isos. So let's go back and number them. When you see an iso pattern, but you have 1 carbon in between before it starts, 1, 2, 3, 4. 4 carbons total means it's a butyl. So that's an isobutyl. So you notice that iso has that sort of V shape. We also could have isopentyl. 1, 2, 3, 4, 5. Isopentyl. And that shows up commonly in nature, so it actually has Another nickname, isoamyl, aka. Okay, and then this is your regular old pentyl, right? Which you would expect to know, but I'm just showing that in the scheme so we can compare them. Okay, so those branches you should be comfortable with adding into a name so that you can name anything, or at least what we'll throw at you for this part of the class. All right, so practice some nomenclature before I want you to have your model kits for the next lecture. If you didn't have them now, you need to have them next one for sure. Okay? All right, signing out.